Hello, welcome back. We are ready to write a complete proof of the weak Mordell-Weil theorem. So remember that last time we had an intermission in algebraic number theory to prove this result right here that says that the maximal extension of a number field, that is a billion, unramified outside a finite set of places, and of exponent m for some fixed m, that is a finite extension. And we use that, we're going to use that to prove the weak Mordell-Weil theorem. We already sketched how last time, but I want to go over it in a little bit more detail again, just to show that we actually can extract a bound on the rank of an elliptic curve given given all this information about the number of places we need and so on. So here's what we did for the proof then of the weak Mordell-Weil theorem. So because of the existence of the Kummer pairing, the Kummer pairing implied that what the weak Mordell-Weil group, that EK modulo MEK, is finite if and only if the extension or the Galois group of L over K is finite, where remember that this L for us is the extension that you get when you find all the mth roots, so the pre-images of points in K via the M multiplication by M map. Okay, so this is what the Kummer pairing tells you, that the Mordell-Weil group, the weak Mordell-Weil group, is finite even only if this extension L over K is finite. And then we also showed that this L over K is unramified outside a finite set of primes, outside a primes S. What primes? We had to throw in the infinite primes. We had to throw in primes of bad reduction for E over K. And we also threw in there primes where primes that divide M. Okay, if you factor M times OK, the prime ideals that divide that, we don't want those either. But all this is a finite set of places of K. And since then by the proposition, L or K is contained in L is contained in that maximal abelian extension. Is unramified outside S, and abelian is abelian, and unramified outside S, and exponent M, and unramified outside S. That was something we proved also in the previous lectures. And then since this is finite, from here to here is finite, that implies that L over K is finite. And therefore, again, by the Kummer pairing, the weak Mordell-Weil group is finite. Okay, so that is the proof of the weak Mordell-Weil group. Remember that to prove the Mordell-Weil group, the Mordell-Weil theorem, what we'll do next is say that if we have a high function with some properties, we're then going to be able to prove the Mordell-Weil theorem. So we'll do that next, but let me go back. I want to show you that This proof is not just saying in the abstract that this extension L over K is finite. Is actually giving me a bound on the size of the weak Mordell-Weil group, which in turn gives me a bound on things like the rank of an elliptic curve. So so here is some remark on the proof. So and this is part of one of the exercises that appears in Silverman, appears in my homework sets. That this is, I think it's very important, because this is one of those amazing proofs that is not just giving you something like the finiteness of this group, but it is actually giving you even a way to give a bound that is computable for the rank of an elliptic curve. So what we did was the following. First, we supposed that the M torsion is contained in the rational points over K. If it's not, then we have to extend K to include the M torsion. In practice, what we do, so we don't have to increase the field too much, is we try to pick M to be 2. If you pick M equals to 2, then at least over Q is even possible. It's possible that you have the full 2 torsion defined over Q, in which case you don't have to even increase your field for that elliptic curve. If you don't have the 2 torsion, then you increase the 2 torsion, and that's at most an extension of degree 6 of your field. Okay. Now, so assuming the Mordell-Weil group, okay, so assuming the Mordell-Weil theorem, we are going to prove later on that this is the torsion subgroup plus copies of the integers for R copies of the integers where R is the rank. This tells you then that the weak Mordell-Weil group is isomorphic to the torsion modulo M times the torsion plus Z mod M Z to the R. Okay. Now notice that in many cases, when you mod out finite group by M times that finite group, a lot of things are going to cancel. There are going to be multiplication by M is going to be an automorphism of the P torsion or the P primary part for P not dividing M. So a lot of it cancels out, but the fact that EM is containing K means that here there are 2 copies of Z mod MZ that survive. So EM modulo M survives this quotient. So you do have at least 2 copies of Z mod MZ in there. Okay. So that gives you that the Z mod M rank of the weak Mordell-Weil group is going to be 2 plus R. Okay. There is another exercise in the homework set about understanding what happens in quotients of abelian groups, of finite abelian groups, when you quotient it by M. What is the size of that, and what survives and what doesn't, so you understand what's happening there. Okay, now we also have the Kummer map, the Kummer pairing that goes from E to the non-degenerate pairing, the perfect bilinear pairing, like this, which is perfect. And we actually know that this is perfect, and that one of these is finite. So they are both finite. The EK mod M is finite, as it is the Galois group of L over K is finite. And then these injections that we got from the perfectness of the pair, they actually are isomorphisms. Okay, so then EK mod M EK, it doesn't matter that it's an isomorphism, but because we're going to be doing bounds. But in any case, we have an injection into the HOMS because of the perfectness we have an injection in here. Okay. So now to compute the rank or to give a bound on the rank of the elliptic curve, what I need is to know how many copies of Z mod MZ are there in this home. Okay, but this is isomorphic to the home of the Galois group of L over K, and this is just isomorphic to 2 copies of Z mod MZ, so might as well put them here. And then the homes from here to 2 copies of Z mod M is the square of the home, so it's home cross homes 2 Z mod MZ. So do 1 copy and 2 of those. Okay. So now what we need to bound the rank is to bound the size of the homes from the Galois L over K to Z mod MZ. Okay. And since the Galois group of L over K, that is a billion of exponent M, I need to know how many copies of Z mod MZ do I have in Gal L over K to be able to bound this. Okay. Now, to do that, we need to know how big is the extension L over K. Now, remember that we are assuming also that K contains the roots of unity. Okay, this was necessary to use Kummer theory, but this actually is implied. This inclusion implies that inclusion by the Weil pairing. Okay, so I'm not increasing my field anymore. I know that's in there. I need to know how big is the extension from L down to K. And what I'm going to do is, in fact, compute a bound for a larger thing, which is the extension from K up to the maximal abelian extension and ramified outside S of exponent M, where, again, S contains the bad primes, the infinite primes, or places, and places dividing M. Okay. So if you have an elliptic curve, you can compute this number. This is not hard to do. You just have to see how many primes are dividing M. You factor M times OK. You can compute the number of infinite primes. That it's, if you know the degree of your number field and you know the number of embeddings, then you know the number of infinite primes, and the number of bad primes are prime ideals dividing the discriminant. So this is very easy to compute, this set S. And in fact, it's easy to compute. What we need is actually the quantity of these places. Okay, so now by what we said is that by Kummer theory, this extension K ab SM, that's a bad S, is in fact K adjoined mth roots of A, where A is in some class of mth roots, or class of M of numbers modulo mth powers, where TS was classes modulo mth powers, such that the order of vanishing at nu of A is 0 modulo M for all nu in finite places not in S. Okay. Now let me go to the next slide. Again, now what I need to know is how many of those units, how many of those elements A do I have to have in TS so I can increase, so I can get the maximal and ramified extension outside S that is a billion exponent M. Okay, so what we need now is to bound TS. And what we did was write a map from the S units to TS that sent a unit A to A modulo mth powers. And I have not increased, remember, I increased my set S in the proof. I increased the set S, so RS was a principal ideal domain, right? We actually don't need that much power. We want this to be surjective, but for that, remember that what we did is, given A in TS, I wanted to see that it's coming from something that is actually a unit. And what we did is, well, then if you look at this, this is an ideal. This is going to be, by the factorization into prime ideals, it's going to be the mth power of an ideal. And what I need is for B to be principal. I don't need every ideal to be principal. I just need the ideal B here to be principal. Okay, so I need for this to be surjective, I need such ideals B to be principal. But you see, B is in the is an element of order M, or dividing M in the class group, because B to the mth power is principal. Okay, so since the class of B is in the mth portion of the class group of K, I don't know how big the class group of K is, but this will be the mth torsion will be some copies of Z mod M. I don't know how many, but again, this is something that we can compute. If we have a number field, we can compute the class group and see how many copies of Z mod M Z are there in the M torsion. But again, you see now I'm doing it a little bit better than before. I'm not computing the entire class group. I'm just computing the mth part of the class group, the M torsion. So now what I need for B to be principal is to add to S every single prime that generates this part of the class group. Okay, so this will be generated, each one of those will be generated by some prime. Okay, up to R, let's say. Okay, that you can find the generator that is a prime ideal for those classes that generate the mth part of the class group. And then what we're going to do is add row 1 through row R to S and get S prime. Okay, so so what happened then is, what just happened is that we have increased S by the following number, by the Z mod MZ rank of the class group of the M torsion of the class group. Okay, so if you look at the rank, I need one prime for each generator of that. So I have increased S by that much. Okay, and then what happened? Now I'm done, because now I have so again, mu M was inside K, was inside L, was inside K, ab, S, M. But when you increase S, you get a larger extension. So this is inside K, S, prime, M, and LS, and again, by Kummer theory, this is K adjoint the mth roots of elements in TS prime now, and the map Rs prime cross to Ts prime is now surjective, and the mth powers are in the kernel. So what we get is that Rs prime cross modulo Rs prime cross mth powers surjects into Ts prime, and therefore the number of generators you need to generate the maximal abelian extension exponent m and ramified outside S prime, this is less or equal to the size of this unit group modulo mth powers. Okay, and the Dirichlet S unit theorem, okay, implies that the rank of R as the free rank of Rs prime cross is S prime minus 1. Okay, so what we've done is this part gives me a bound on this part. How big is this extension? Okay, because I know how to generate that extension. So given that I know a bound on the number of generators of that extension, I know a bound on the degree of this extension, which gives me a bound on the degree of this extension. I know how many, the Galois group here is just as many copies of Z mod MZ as there are generators of this group here, and that gives me a bound on the size of the Galois group of L over K, and that gives me a bound on the number of homomorphisms from Galois L over K to Z mod MZ, and that gives me a bound on the size of E mod M, and that gives me a bound on the rank of the elliptic curve. Okay, so I find this very interesting, and so I've written there in the homework set. There will be, I think, in homework set number 5. There is a problem. Just do this completely. So work it out completely to write down what the bound is. The bound is actually written in the first problem in chapter 8 of Silverman, but this is how you prove it. Okay, so just go through it again and put it together just so you see yourselves what is happening. Okay. All right, very good. I'm going to stop here, and then in the next video, we're going to talk about the descent procedure. We're going to start talking about heights and about the descent to complete the proof of the Mordell-Weil theorem, not just the weak one.